Okay, this is a course on statistical mechanics, and there is a book that I've written. You can kill a man with this, really heavy. That because there is a 4-color, very expensive book, but Institute has got now 6 copies of it, 3 for integrated PhD, and you guys are a little miser. They have got 1, but they are getting few more. So you'll get that. Till now, I am not, though I think PDF somewhere probably available, but producing a book like that, publisher spends enormous amount of money. And all publishing houses are going out of business because of our smart students who don't buy anything. They don't need to buy anything anymore, okay? So, for that reason, and this is expensive, as you see, 4-color and very nice page and all these things. We'll follow this book in toto. Okay. This is the only statistical mechanics book ever written from India. There are some other books which, but they are not quite textbook, number 1. Number 2, they are more for some, I say, subset of physics problem. That means they do a bit of stat mech, then they go into Fermi boson and the those kind of superfluidity, superconductivity, that kind of a thing, which are all exciting. But in chemistry and material science, we don't need them that much. We have our own set of very fundamental and nice problems, which have been not discussed things. So that was one of the reasons to write this book. All my students helped, and it was written over many, many years. We are trying now to do a time-dependent version of that. We have a time-dependent version, molecular reaction liquid, which I probably will use a little bit towards the end. Okay, now this book has 30 chapters. And all of them will not be needed. I would imagine of these, about 15 chapters will be covered. Okay, the other chapters, not that they are advanced, but they are very spatial and specific, so we need not go into them. Now, when you talk of statistical mechanics, there are these 2 things there, right? You have the, nothing is there. How much? How come? Nothing is there. What do you do?
I did not do anything.
Okay. So now, let me see if I get a space, because I cannot do that well. So, this is a thing which is not taught much. One of the reasons of writing the book, and took so much effort to write the book, and in these days, the amount of royalty you get is about, I think something it is doing by itself, is about 1/3 of our 1 month salary. That's the kind of thing it has come to, because nobody buys books. But even though they don't buy book, do that, then it will stay. But the book remains, it gets circulated and goes into people's hand in the digital form, which is very nice. So, chemistry department is not taught that much. One of the reason I first time had the idea, I went to Central College in our Bengaluru University, and I was giving some valedictory or some kind of a lecture, and I looked into their course, and I found that they have statistical mechanics in their MSc, but and they're very nice syllabus. I said, what happened? Well, no, it is not taught. Why? Because there is nobody to teach the course. That happens repeatedly. It has not changed from our time. In the last 40 years, it is almost the same story. And when they teach what we call non-interacting statistical mechanics. That means the very preliminary thing, which we'll do then, because that forms the foundation. Now, let us start a little bit more seriously now. That there are these 2 terms, statistical and mechanics. Now, anybody has any idea why we have these 2 terms? Why we have mechanics we all understand, right? Newton's law. Okay? And that means mechanics means what? Mechanics means mass, velocity, acceleration. Newton, however, did not formulate his in terms of energy. That's one dichotomy you should always say. But our quantum mechanics, we always formulate in terms of energy. That's why quantum mechanics was formulated through the Hamiltonian things. So in quantum mechanics, you have a quantum and then mechanics. These two things. So somehow we are doing mechanics of quantum. That is the basic idea, though it's not quite like that, but that's how the name was formulated. It was done to differentiate it from classical mechanics. That's quantum mechanics. This again, we have the mechanics here, but you have statistical in front of it. Why do I need the name statistical? Why? Mechanics is very deterministic. What Newton's law tells you, that if I give you give a particle of mass m, and I give you initial in a potential or in a force field, and I give you the initial position and velocity, then you will be, according to Newton's law, you will be able to predict the trajectory and the motion of the particle future all through exactly, right? So that's why classical mechanics is called deterministic. You guys know these things? Now, then classical mechanics is, we grew up by thinking it is deterministic. Then what statistical doing here? Very good. Yeah. But probabilistic thing in quantum mechanics is very inherent, which is always there. But we are not going to do quantum mechanics. We are going to do something like how to describe water in that you drink, and we want to understand its transition, how it becomes ice. We want to describe how rains form, and we want to describe, for example, how protein in your body folds. We want to describe how DNA functions, which is one of the most important areas of research in statistical mechanics now. In all of them, quantum mechanics, it's okay. I think I need probably a little bit bigger room. Okay. In all of these, you really don't need quantum mechanics. Okay, quantum mechanics is always there in a different form. Quantum mechanics gives you how the particles interact. But once that interaction is given, you don't need quantum mechanics anymore. You still need Newton's laws, laws of motion, or classical mechanics. The reason this statistical comes because if you try to solve Newton's equation, and this is something where a course in classical mechanics is very, very useful, then we cannot solve anything beyond a two-body problem. So this is something really most students don't realize, that if I have two particles, A and B, and they are interacting with a force, which depends on the distance between them, and that force is arbitrary, I can solve this problem. Most of the time, this force can be very complicated, because force is a potential, this is a gradient, ddr, derivative, and if my potential between two is the simplest realistic potential, R, this goes like that. This is called Lennard-Jones potential, which has the following form. Sigma is the diameter. These are the parameters one gets from quantum mechanics. Also, one can get it from experiment. These kind complex form, these are, as I'm saying, this is the simplest. Like for noble gases, for argon, For that, we cannot really get an analytical solution that tells me how A and B moving with respect to each other. It's very important. We can reduce it to a quadrature, but we cannot solve it. Now let me see, I put one more particle here. Particle C. Then I just can't solve it. So we say that even a three-body problem cannot be solved. Nobody has been able to solve a three-body problem. So you are faced with a difficulty now that you are having Avogadro number of particles. Your aim is to describe something like acetonitrile, water or ethanol. You want to describe a protein which is a pretty big beast with all the amino acids or a DNA, and you want to have this protein not in isolated condition, you want it in water or in your human body with their ions also. So you are having this huge number of particles that are interacting with each other with a fairly non-trivial force field. Have you heard the term force field? When I use something you do not understand, please ask me. Force field means the particles, they are F, how they interact. Okay. So you are faced with this difficulty that we cannot solve a three-body problem, and we have to solve this Avogadro number of particles, or even more, even 1,000 you can see is impossible to understand, to describe nature or natural phenomena. Given that situation that we cannot do, it was then long ago when people tried to do, you have heard the name of Boltzmann, the great Boltzmann and Boltzmann's equation and all these things, Maxwell, right? So the person who first introduced was Maxwell. Maxwell tried to describe the velocity of particles. Now he realized, he was one of the highest form of genius who died, I think, some 37, very young. And in that he did one of the biggest achievement, which is the electromagnetic theory. And then, of course, many other things he did. A lot on thermodynamics. Now, Maxwell realized that, look, if I have this room, and in this room I have lots of oxygen and nitrogen moving around, and I want to know how oxygen and nitrogen, what are the velocities of them. And he realized that if I want to describe it in terms of Newton's laws of motion, that's what everybody was using those days. Though there's a beautiful branch of hydrodynamics was being developed at the same time, and the probability theory was already developed by mathematicians. So Maxwell realized that I cannot do the usual way, the standard classical. So he introduced the concept of probability. So first time in the classical mechanics sense, a probability distribution of velocity was introduced. That was done by Maxwell. So he realized that it is meaningless to think of one velocity of one particle. Instead, it makes sense if I want to calculate the pressure, I want to calculate the viscosity of a gas or equation of state. It makes sense to now saying how many molecules have velocity between v and v plus dv. And that's Maxwell PV, right? E to the power minus half mv square. Boltzmann was so taken up by this beautiful paper of Maxwell that one paper he carried till the end of his life was that one single paper of Maxwell. It was like a Bible to him. He always, wherever he used to go, he used to carry that one paper. He realized, however, there is a dichotomy and a beautiful dichotomy actually in Maxwell's theory, which is that Maxwell had to assume collisions in order to equilibrate, in order to calculate the pressure. There are collisions. There are elastic collisions, he assumed. Remember, in kinetic theory of gas in first year of BSc. So, but however, if they don't have any size, if they are really ideal gas kind of things, then the way you rate kinetic theory of gas is essentially like an ideal gas. They are need to be a size, and we have to describe the collisions. Then Boltzmann set out to do a theory which is called Boltzmann-Kinetic equation. And many things came out of that, like entropy, S equal to KB, ln omega, and many other distribution function, concept of distribution function in a molecular picture. Everything came out of and came from Boltzmann, that beautiful series of beautiful work that he was criticized heavily because he introduced probability concept. See, Maxwell kind of left it at the distribution, but Boltzmann tried to take it one step forward. He wanted to bring Newton's law into the world of atomic physics. Atomic physics itself was at infancy at that time. But he couldn't do it because he had to introduce some probabilistic concepts which called molecular chaos. And he was heavily criticized. It is often said that he kind of committed suicide because of criticism. Somebody says he was, he just drowned in a river, whatever. But it was Boltzmann and Maxwell who together realized that we cannot go very far by mechanics. Boltzmann tried, the poor guy really tried, to go into in a really rigorous mechanical way, describe the statistical phenomena, the equation of state or pressure, but he couldn't do it. He had to introduce the probabilistic concepts. So probabilistic concept in description of natural phenomena of many particles, we call it statistical mechanics, is called the many body physics. That came because of Boltzmann and Maxwell. What Boltzmann and Maxwell was doing was watched with a huge concentration with one person across the Atlantic who realized the immense power of this thing, because he was trying to understand thermodynamics. His name was Willard Gibbs. J.W. Gibbs. Josiah Willard Gibbs. And the Gibbs is the guy that used to give thermodynamics or gives free energy, gives Joule equation, all these things is the same Gibbs. Gibbs realized that how to do these things a little better. That we'll discuss only. So this is the beginning, how statistics came to be combined. Statistics and probability came to be combined with classical mechanics. Basic goal of classical mechanics was kept. However, I think we need to do something about this, because we cannot afford to have this. This never happened before. Why it is happening? Okay. No, I think whenever one is not doing for long time, then so I have to go back and forth like this and like that, then it's okay. All right. So, okay, right. So, I'll now set out the course, because after all it's a formal course and a rigorous course. So, we'll talk what we are talking now at the preliminaries, and today will be preliminaries. I'll set out the goal. I'll try to convince you why you need to do statistical mechanics. You should never do anything unless you are convinced, okay? And why you need it, okay? And as we need certain amount of statistics, we'll do a one lecture on probability and statistics. Some of you might have done. I know in class 12, they have these days CBSE syllabus fairly good on probability and statistics. It will be not too much more than that, but we'll refresh our memories. Then this will be a very nice chapter, which is on, I'm following the chapters in the book, Fundamental Concepts and Postulates of Statistical Mechanics. Now, this is something we will not do, the Liouville theorem and Liouville equation. This is, in the probabilistic description, is the equivalent of Newton's equation. What Newton's equation has, Liouville equation has exactly the same amount of information. But we might just, I'll show you, but I'm not going to talk about it because rather complicated. Then from here comes the most important thing, why statistical mechanics is not taught in chemistry in India, while abroad in United States, you will find if there are 10 theoreticians in a chemistry department, then 5 or 6 of them statmen. That's the kind of thing. When I was doing PhD postdoc abroad, the 10-year period, there's not a single quantum chemist was hired. Everybody was statman. That was the great push towards biophysical chemistry and biophysics. Even now, the scenario is very much like that. In physics department, of course, it is always the many-body physics, and a majority of the people are doing some kind of statman, quantum statman many times, because all their phenomena, whether superconductivity, semiconductor, everything you need to take into account interactions. Whole superconductivity, the BCS theory is bosons out of Bose condensation, which is a statistical phenomenon, formation of a coherent state. Without statistical concept, you cannot understand. And I know there's a large number of in chemistry which are organic chemists, but even in organic chemistry, it is that you would need little bit of understanding of thermodynamics. Okay. Now, ensembles and partition functions is where the machinery is being set up. This you can consider the postulates are the postulates of quantum mechanics. You can have the analogy. And this is where you can consider kind of partition function is kind of your Schrodinger equation. Then this very important thing that fluctuations are response functions in equilibrium statistical mechanics. The response functions are your specific heat, isothermal compressibility, and dielectric constant. And these response functions, the way your body or a system responds to external perturbation, that is the response function. That response function are determined by this is one of the most beautiful thing of entire physics, are determined the fluctuations of your system. This is just amazing. Have you wondered, let me ask you a question, why specific heat of water is 3 to, I think, more than twice, maybe 3, but probably 0.41 and 1. Why more than twice, specific heat of water is more than twice of acetonitride? Water is very small, smallest molecule, right? 2 hydrogen, mass is 1 and 1 oxygen. Right, little bit more.
Because when we heat it, the energy goes transformed into the vibration energy of the hydrogen bond.
Right.
So it can have more heat. So you should give more heat to increase its 1 degree.
Exactly. That little bit is an excellent answer, actually, very good answer. That because of the hydrogen bonding, you bring in certain extra modes. One of them is this excitation. So hydrogen bond has around 200 centimeter inverse, which is 1 kBt. Very significant. Why water plays such a role, there are many reasons for that. One of them, this excitation is 200 centimeter inverse, and 1 kBt 300 Kelvin is 206 centimeter inverse. So this is my oxygen, this hydrogen, it is doing like this. Even though hydrogen bonded, that is 600 centimeter inverse. And then it has, because of the hydrogen bonded structure, it rattling around all the time within a cage. That happened at 50 centimeter inverse. So these are what we call low frequency spectrum of water. And you are 100% correct that when I try to give, I see specific heat, the amount of heat I have to give to increase the temperature by 1 degree. Now when I give heat, then that goes into all these modes. So you have to populate these modes before you can increase the temperature. Acetonitride doesn't have them. It has a rotation, but doesn't have hydrogen bond. So this, though acetonitride is so much heavier than water. Water has no reason to be a liquid. If it didn't have the hydrogen bonding, it would not have been a liquid. Okay. So that's now. How do I quantify these concepts that we are talking? That what's your name? Huh? Otondito is shortened one. No, Otondito. Everybody calls you Otondito. Otondito. Oh. What your father or mother tells you? You don't want to tell that. Okay, what Otondito? You have to forgive me. I'll get it right this time. Told us that the response function of, but these are words. What I'm telling you are the words, but we need a theory to quantify. We need to have a way to really calculate the specific. Okay. What the beauty of one of the first in my book I probably removed it, is called the delivery of the promises, is that statistical mechanics gives you expressions of specific heat, thermal compressibility in terms of the fluctuations. So specific heat turns out to be mean square energy fluctuation, one of the most beautiful relation of the whole entire natural science. That your body, your response, that goes even to an equilibrium case, is determined by what you want, your natural motion. Okay. So the person who are excitable responds very fast actually has the kind of excitable thing. That also goes in the level of molecules that which have all these excitations themselves, they have larger response. That goes also to dynamics. So these are very important chapter in the book and will be important of the course. Then we'll do what we learned here. We apply to ideal monatomic gas, and we'll see that the ones that you derived in your kinetic theory of gases, they follow very simply from without invoking the Maxwell-Boltzmann way of derivation. How the PV equal to KBT, CV specifically equal to 3 by 2R. All these things follow from these partition functions which we introduce here. And we also get an expression of translational entropy. Okay. Then we'll do, so these are the kind of a noble gas, argon, krypton, neon kind of thing. Now we'll do diatomic molecules, and there we'll try to understand that how one talks of vibrational entropy, which we'll need in all the properties, and rotational, and then specific heat contribution of these modes to these things. As I was telling, we need these modes to understand the specific heat or any other response functions. We'll do quantum statistics, Bose-Einstein condensation, that because this is the usual course, though it is a beautiful thing and good to know, but we'll little bit sit out of the thing. Then we'll do little bit of the Ising model, but very small amount of Ising model. And we'll not do these things, these are from there, but we'll jump and we'll go to phase transition. The first and second order phase transitions and why things happen, why ice melts to water when you have above 0 degrees centigrade, or how water goes into ice, and all the kind of phase transitions that are all around us. We'll talk about the phase transition. Then we'll do another very beautiful thing, which is Landau theory of phase transition. And with this great physicist Landau, he introduced certain concepts which went on to become paradigm of physics and chemistry, which is the order parameter, the concept of order parameter. We'll have a little bit of critical phenomena. Phase transition, now it are completely gone. Okay, again, it will come back by itself if I wait. Okay, I have to do like that.
Sometimes that works.
That I can do. Okay, so then we will do, so Landau theory has certain phenomenology, we call it phenomenological theory. So we'll do little bit of little difficult things, which is Mayer's theory of condensation, because that gave rise to many important concepts, and that's about it. Then what we'll do, little bit of melting or freezing, but not too much. Then little bit of nucleation. These will just not even give one class or maybe one class. Okay. But there will be one part we'll spend quite a bit of time is the computer simulation methods. And because that is what is more appropriate in modern times, that students must learn how to use computers to simulate the properties of liquids and solids. So have you been, anybody taught computer simulation to you? nothing of computer simulation. That should have been done actually, because should have been done long ago. I think these things should be taught in 11th or 12th grade, because this is something what you carry forward, whether you are becoming organic or inorganic chemist or whatever, and of course physical chemist, then you have to, and biophysical chemist or biophysicist, you have to do computer simulations. But computer simulation you cannot do if you do not have these things. And also it's not too useful if you do not know Landau theory of phase transitions. So they are all beautiful subjects. You can take the book, and the books, I think, library, there are 4 copies now, some more they are buying. They wanted books from me, but I myself have just 1 copy because I gave everything. So then there is use of this in calculation of free energy. This part of the course, one Professor Eshwanath, who does computer simulation, did all his life, he has agreed to teach, but he travels a lot. So if he teaches, fine, otherwise I'll teach, but we'll see how it goes. But that would be an important component of the course, to teach you guys how to do computer simulation. Okay, again, let me do myself. No. It's becoming a lot of fun though. Oh no, I think it has got angry because I hit it. Okay, so you can fix it by the time. Let me continue. So now what I'll do, basic, we have to either use a different computer, but my computer never does it. So why is going here? No, I'm not pressing anything. I'm just pressing what I press. Okay. So now one thing.
So the slide is over.
The slide is over. Oh, that's what. That was easy. Now what is the next one?
It's open over here. Named Preliminaries.
Okay. So now, actually, this is right. So now, what we'll do, let me use this one. So we'll do the following thing. I'll tell what are the scopes of statistical mechanics. It's very important that we know, as I was giving you a few examples, melting of ice and these things. So these are the huge number of things that we use statistical mechanics for. And these are many of us really work on that in chemistry departments, on a materials research laboratory. So look at that, how many huge number of, we do liquids and solids, we do complex liquids, binary mixtures, all these things. Then we do chemical, another thing, chemical reaction, which I want to do last 2 class of the A is the chemical, different kinds of chemical kinetics. Then you see all these kind of many different kinds of I can read it better for me. So this I was saying, phase transition, nucleation, critical phenomena. Then you have chemical reactions, binary mixtures. Then you have this is becomes very important because this what you learn here, and it was done by Debye and Einstein, that went on to become a cornerstone of solid-state physics, normal modes, that introduced by first time done by Einstein and Debye. And then they told you that, how the Dulong-Petit's law, or the why specific heat of solid, they behave as they would behave. So all these things come out from the statistical mechanics. So you can see I have done a very limited thing, but the scope of statistical mechanics, the one that will be relevant to our class here, is enormous. Okay. So in this class, if you can get a glimpse of the things that can be done and can appreciate the power of the subject, that would already be a lot. And then how to do certain calculations will be really useful. Okay. What is that? Oh, you have to take attendance. Not bad. I have not done that for a long time. Okay. Now, scope of StatMech, then essentially, I'll go through quickly some of the things which are not really. One is the binary mixtures, Raoult's law. I don't like this too much, so let me use the board. You know, this is okay for A but not. My computer will die, but that's okay. So, see, one of the things if you do in your physical chemistry, undergraduate physical chemistry, then what are the chapters that we do? Okay. One is thermodynamics, which is entropy, free energy, specific heat, second thing we do rigorously in undergraduate physical chemistry is kinetic theory of gases. Then we have solutions, binary mixtures, Raoult's law, remember? Then we have phase equilibrium and phase transition. Then we have electrochemistry. Debye-Huckel theory. Then we have others, but these five will do for me for the time being. So now in thermodynamics, first, second, and third laws of thermodynamics that we do. Then we want to develop entropy and free energy and specific heat. If you think of thermodynamics, what is the most important thing that strikes you as a thermodynamics? Or few most important or very characteristics of thermodynamics? Absolutely. Wonderful. Now, that has both good and bad. Now, the one good thing is that when we talk of thermodynamics, if you see that it is all came from human effort to do something and failed. So, it are all laws of negation. We tried to create energy, we could not. Came the conservation of entropy. We tried to create the perpetual machine of the second kind. We could not. Came the second kind. Okay. So these laws of thermodynamics then gave us our failure to convert energy completely 100% into heat, gave rise to the concept of entropy, and that went to free energy. The name free energy is very significant because it is energy free to do work. That's a free energy. But if you think about, so the first thing to know is that it is macroscopic properties. B is the laws of negation, and it gives me relations between entropy, free energy, but it does not allow me to calculate anything from first principles. It does not allow me. It actually has very little quantity power. So first law and second law gives you some relations between thermodynamics, entropy, free energy, all these things. But now I want to calculate entropy. Why I want to calculate entropy? I want to calculate free energy. Why I want to calculate free energy? Because if a process is happening, it will go spontaneously to the lower free energy. So in order to know that, I need to know that free energy of one state is more or less than the other. Now, how do I calculate the for example, they take the simple thing, the ice melting, then what happens? The free energy, if this is ice, and then I go above 0 degree, then this is liquid water. So when temperature is say 5 degrees centigrade, this is the free energy, and in one of my order parameters, we can out it density. My order parameter I take as density. Board is not very good. My hand is not working. Okay. So it goes over to that. Okay. Now tell me, how do I calculate now the free energy of ice and water? This you know, right? You have very much done it in your schools that I think it comes from school that free energy, it happens spontaneously. It goes from higher to lower free energy like chemical potential. So that's how chemical potential is introduced. Now tell me, how do I calculate free energy? No, I want absolute free energy. Well, if you cannot give that, give me the change.
Consider this as a combination of different processes, that is from the lower temperature to 0 degrees and the combination at 0 degrees, then from 0 to 5 degrees centigrade.
Great, very good. Now tell me, you are telling something, because this that okay, it is partly correct, okay, or partly of what I wanted. So yes, so where do I go back? How do I start? Where my definitive state? That's for gas only. Now, you think thermodynamic SPTV, that kind of thing? No. Anybody should make an attempt. Okay. This was the paradox faced by people, and then Max Planck, that is why Max Planck came up with the third law. And one had needed to introduce a reference state. And reference state is the perfect crystal at absolute temperature. That gives you entropy equal to 0. Then I follow what you are saying, that I heat it, solid goes to melting. Now tell me, actually this is the answer I want now. If I go, say ice, 0 degree to 273 Kelvin, I want to calculate the free energy. What is the free energy of ice at 273 Kelvin? How do I get it? We have all done it, because this is one of the things we do in undergraduates.
So we know the reference state, so we can integrate any differential equation of gives free energy from 0 to that desired temperature.
That's not how we do it. There's a very definite way of doing it. There's a definite way to get enthalpy and entropy. What is the equation?
You mentioned a reversible pathway and then
No. Yeah, if I have to go from 0 Kelvin to 273 Kelvin, there's a very definite way we do. Anybody on the right hand side, left hand side guys are doing better than you. I have to populate the right hand side. Exactly. Yes. So you integrate Cp by T and you get entropy, and you integrate Cp, you get enthalpy. Right. So though you need this specific heat. You need this specific heat. If you have this specific heat, then you can get the enthalpy and entropy, and you can get the free energy of ice at 273 Kelvin. Okay. Now comes the crunch. This brings you to 273 Kelvin. You have the free energy of ice. Now it melts. Goes to water, latent heat. 80 kilocal per mole, 80 kilo per gram, right? Now tell me, how do I get the latent heat? Ladies, how do I get the latent heat? For that matter, how do I get the specific heat?
So as ice melts to water, so this is equilibrium. So delta G of the process should be 0. So delta H equals minus T delta. So that delta H is the latent heat.
But how do you get it?
T delta is become that delta is equal.
See, when I am going up, I don't see any problem up to 0 to 273 Kelvin. I have no. Though I have little bit of uncomfortable feeling that I have to get the specific heat from at every temperature, do experiments, but there are, you must have done in your Castellan or Moore or Glasstone or whatever Atkins, that there are beautiful expansions of specific heat in terms of temperature. A0 plus A1T plus A2, then B0 plus B0 by T. They put everything, both proportional to T, inverse proportional to T, and you get the number. That is given in many handbooks. I'm not happy with that, but I'll go with that. But I would be rather happy be able to calculate, which Einstein taught us how to calculate, and by Einstein, that specific of solids. That again comes from statistical mechanics, and that we'll do when we do actually pretty soon. And that's the one very important piece of result from statistical mechanics that comes very early. But I live with that difficulty. I live with that limitation that I cannot calculate it. I experimentally measure. But then again in the latent heat, I have to experimentally measure it. I can calculate. There is a difficulty. This is more stable than that. I can go and I calculate the entropy and specific heat of these things and enthalpy. But here I cannot because I have no reference state for this. I'm just giving a paradox. Okay. So that's why phase transition, the amount, the number we said 80 or liquid water to steam, that is some 537, right? That those numbers, change of density, why ice is Titanic, you remember? Why ice is so much lower density than water. This is significant, 10%. It's a big number. And that's what created a lot of problem, right? Now, so the many aspects of thermodynamics remained I'll say ill understood or incomplete. One of the things is that it does not really has a good calculational tool. Okay. And that was what provided by statistical mechanics. That's an important, enormously important thing. Then comes kinetic theory of gases, Maxwell distribution. And however, kinetic theory of gases that you read is again goes for ideal gases, PV equal to RT. But if I go to dense gases or interacting gases like this in this room, or nitrogen and oxygen, kinetic theory of gas is not applicable. Kinetic theory of gases does not phase transition. If I plot pressure PV, remember if I plot this, V versus density by 1 over G, then this is ideal gas. PV equal to kVT, NkVT. So I bring V on the other side, 1 over V or rho, then I get a direct straight line. But real experiment doesn't do like that. Real experiment, I don't have any other color. Oh, here. Okay. So real one actually does. This is the real thing. If you remember, Maxwell goes like that, and this is the tie line. So if this is the real thing, Van der Waals was wrong, Maxwell correct. Okay. But that's not quite important now. Important is that it does not go like this. It doesn't go like ideal gas. How to explain that? See, it was left in undergraduate. It was left completely, unexplained. Why it happens? Why ideal gas? We say okay, because things are not ideal because they're interacting. Why? They're interacting. What? Interacting by what? An interaction potential. If there's an interaction potential, then how do I include that effective interaction potential? That means how do I quantify? How do I go beyond kinetic theory of gases? Okay, that is, again, you come back to statistical mechanics. That's one of the first things statistical mechanics does. Okay. Then we have solutions. You have Raoult's law. And you have non-ideality. Breakdown of Raoult's law, right? Remember what is non-ideality? A property P, I put in a mole fraction of A, then Raoult's law will be saying that x1, xa PA plus xb PB. Remember Raoult's law? But it never happens. Most of the time it goes like this or it goes like that. We call the breakdown of Raoult's law or non-ideality. Again, in your undergraduate physical chemistry, no explanation is given. And again, can you guys make a guess why these things happen? Why? They are non-ideal. For that, you have to first ask, when are they ideal and why they are ideal? When I mix two solution liquids A and B, let's say water and acetone, I mix. I use ethanol and water, or dimethyl sulfoxide and water, whatever we have. These are the things we work, that's why that the name come to my mind. Then, why they are not ideal?
The delta H mix is not equal to 0.
Exactly. Very good. So now, why the ideal delta H mix should be is 0? Why it should be 0?
Because when it's collide, there is no energy loss for ideal case, but for real case, there is a energy loss.
Yes. That means when the molecules are next to each other, surrounded by, if I surround by A or surround by B, it does not matter. It stops there and it's correct. But now you want to know it more precisely. I want to quantify this non-ideality because that's very important. Because in chemistry, we all use solutions all the time. Their solvents are extremely important for any chemical or biological reactions. Okay. You have done, we used to do endless amount of titration. I don't know what is in the game now. Till 9 o'clock in the night. Start at 1:30 or 2 o'clock. And we used to get yellow with hydrochloric or nitric acid. Those were torture at days. And Presidency College, girls never came close when you were near us. They said, you guys can stink, So, so we all work with solutions all the time. Okay. So, solutions are not ideal. If they're ideal, they would have been useless much of the time. Sometimes they're okay. But, so we need to understand it. Now, you tell me, when I mix an A and B, delta H mixture is negative or positive, depending on that. This will be up and down. Why?
If heat is released, then
No, you are saying the same thing. It's called tautology. When you repeat the same thing. Very easy. All of you should know the answer. All of you know the answer. Interaction potential. Exactly. So again comes the interaction potential. Again comes that A and B, we need to describe how they are interacting with each other. I again go to interaction potential. Those are not in your undergraduate textbooks. So we need to describe, at least at this course, we will do a semi-quantitatively to try to explain how we start addressing these issues of A and B, preferentially attractive, as he said, or preferentially they don't like each other. When they like each other, we call them structure maker, and when they don't like each other, we call them structure breaker. These are the terms we use in our undergraduate physical chemistry. But how the structure forms, what are the structures, what are the solvation properties of these binary mixtures, that need to be understood for having any predictive power. So that's an important thing that we try to do, to understand what is going on and why they are and how they are happening, so that we have a predictive power. We can design better things, which is actually now happening. People are doing antibiotics, and they use statistical mechanics to understand drug DNA interaction, and what drug should go in DNA and bind in which way, what is more preferential. They are all coming from now. We have to have the drug and DNA in maybe water, and we have to understand how the drug DNA interaction goes on. And these cannot be done. It uses all the principles of statistical mechanics, power of statistical mechanics, but it is done through now computer simulation. Though there are a lot of work that goes on before that. Okay. So this is the solution. Now phase equilibrium and phase transition. This has been actually, you have the phase rule, Gibbs phase rule, F equal to C minus B plus 2, which allows thermodynamics, the conditions of chemical equilibrium and the components and all these things. Now, however, as I already addressed this, there is a huge number of phase transitions in this world, and huge amount of, and there is a huge problem why rain doesn't come. I was in this one of the Arab countries, and there is a big industry of seeding to get some rain on the poor guys. They have desert. Not bad life actually, going on camels and eat dates, but it gets a bit boring without water. So you need to understand how rain comes, and then of course the horrible problem of now global warming and ice melting. There's a lot of trying to understand what happens, how it happens, and every other. You see, for example, your semiconductor, when you are doping with arsenic or phosphorus, you are doping silicon. That's the whole semiconductor industry. Then you have to tap excess of them into N and P type materials, the junctions, and that is done by very quick crystal growth. That one of the things that StatMech does is they tell you how the velocity of crystal growth happened. Then of course these superconductivity, then order disorder transition in metallic alloys, all this comes under this phase transition. Okay. So phase transition becomes a very important area, but phase transition cannot be done, we cannot understand it at all unless we start and build up a formidable theory. And that formidable theory, as I said, starts with certain postulates. Before that, probability and statistics come, and from the postulates we go to these ensembles, and we go to partition function. Then I'll be start telling you what are the expressions you get entropy, what is the expression that you get enthalpy and free energy. Okay, those are the given by those expressions that you do. Then of course another is electrochemistry. This is a very industrially relevant thing, because we have to have fuel cells, and all battery and cells are based on electrochemistry. And you have read one thing again in the Debye-Huckel theory. Remember the Debye-Huckel theory? Can you tell me what is the Debye-Huckel theory? He started writing the equation. Yeah. Tell me what is.
Determine the activity of the components in an electrolyte solution.
Exactly.
In order to do that, you have to consider the electrical effect, the electrostatic effect caused by the component.
Remember, there is one important thing in Debye-Huckel theory, an ion atmosphere.
Yeah.
Okay, and the ion atmosphere tells you how molecules are arranged around about sodium ion, how many potassium ions are arranged, and then we have e to the power minus psi r. So you are using there the basically basic Boltzmann distribution and statistical mechanics. So in electrochemistry, because of Debye-Huckel theory, you had actually first glimpse of statistical mechanics in it. It goes on to getting Debye-Huckel-Onsager or Debye-Huckel laws of conductivity. That you have studied in Castellan has that. What is that? You two keeping quiet. What is Debye-Huckel-Onsager theory of conductivity? That I think was taught, right? In our time it was taught. This integrated, what the integrated, not PhD student, these BSMS students. Who are BSMS? Raise hands. How many BSMS students are here? Only one? 2, 3, 4, 5, 6. Okay, now tell me, what is Debye-Huckel? You must have taught. Lambda equal to lambda naught minus A plus B lambda naught over C. Okay. How this was derived? Two terms. One is when I have an ion and try to put electric field, try to move. Exactly. Then the atmosphere get distorted. That gets one thing, that is an atmosphere effect. Other thing, the ions move in the opposite direction, they exchange momentum, and that's the electrophoretic effect. Okay. However, in order to do a good job on these things, you need to know really more microscopic level ion plus minus sodium and chloride, sodium chloride distribution. How they are distributed with respect to each other. Then they introduced a term called radial distribution function, which was approximately done by Debye-Huckel. Okay. And the Debye-Huckel theory, however, breaks down at even less than 0.1 molar. It's highly, this is called limiting law. Remember, it's called limiting law. And it's really limiting. It doesn't work anywhere. It breaks down completely. When you plot lambda equal to root C, then I plot lambda as root C, then that thing, as root C increases, lambda naught, it should go like that, but it does not do like that. It goes quite differently, and it breaks down at even 0.1 molar or so. That again needed the intervention of statistical mechanics, and a lot of work went on in 80s and 90s or even now to understand the electrochemistry. So I just gave you 5 examples of things that you know thermodynamics, you know kinetic theory of gases, you know solutions, you know phase equilibrium, you know electrochemistry. So what I am trying to tell you now, all through that your entire physical chemistry, with the exception of spectroscopy and quantum mechanics, is essentially was left unexplained or poorly explained with hodgepodge concept like the solvation cell, iceberg model, then all these kinds of picture, but no understanding. So entire physical chemistry, solutions, phase equilibrium, so boring. All of us hated that. That because it's just certain kind of gathering of phenomena, gathering of certain experimental results, without the due understanding. Something should not be taught really, but then on the other hand, sometimes phenomena and gathering of experimental results should come before the understanding. But you have to accumulate facts to get and things into it. That's the kind of synergistic approach. StatMech, on the other hand, gives you what is called analytical approach to the field. You know, saying why and how that it gives. So let me ask you one more question. I said 2 things. You really I left out and saying it does not come under purview of StatMech. It's only two things. One is undergraduate, our time was not done. Now I think it is done. Quantum mechanics. But one thing we had done was spectroscopy. And what is the relation between quantum mechanics and spectroscopy? After that, we'll stop. What is the relation between quantum mechanics and spectroscopy?
So we can describe the spectra from the idea of quantization. Otherwise, we cannot describe the spectra.
Well, little bit more.
Quantum mechanics actually the different energy states.
Energy levels.
So the spectroscopy, that is the wavelength of the light, which matches with the energy difference between energy states.
Exactly.
Then only we get the speed.
A resonance condition. So, if you have noticed that quantum mechanics came almost hand in hand with spectroscopy. Bohr's theory was done to explain which series? Balmer series. And there were the lines. And so those lines made that they are energy levels. So that led Bohr to postulate that they are stationary states. That is the states that must exist. Two states and I can exchange. And he derived his beautiful theory. So if you look at cause and effect, then black body radiation, which is essentially was the phonon spectrum and the density of states of phonons. One was doing statistical mechanics, which was kind of coming around that time, Max Planck. So black body radiation was not explained by using the classical Lenz law, right? And then to assume the Max Planck had to assume. So it's very interesting to always look at the history, how certain critical observations lead to development of certain seminal work. So quantum mechanics was developed to explain the spectroscopy. And statistical mechanics was developed to explain thermodynamics, phase equilibrium and kinetic theory of gases. So it is good to remember, it's always good to remember, and the thing that you know, which I assume all of you know, quantum mechanics and spectroscopy. StatMech has not been taught much of the time. But so you have to always go back to quantum and see, and that's the one theoretical framework that you. So when I give popular level lectures to schools sometimes for this, KBPI kind of thing, I always say that there are these two theoretical frameworks. Two formidable and only two, then nothing else. One is quantum mechanics and the statistical mechanics. And they together form our total understanding of this universe. And they are not disjoint, they talk with each other. There is quantum statistical mechanics, and in statistical mechanics we need the interaction potential that given from quantum, and that is what is called force field and all these things. So you should always think of them, and it always helps, always helps. It was not given to us when we are, I learned statistical mechanics, that it is always good to have an overall picture and a perspective, what you are going to do, what is needed, why you are doing it. If you are convinced of why you are doing and there is a need for it, then you can go for how we are doing it. So I explained to you today why we need this course. Okay. And from the next class, I'll start how we are going to do it. Okay. And that goes through probability and statistics, then the postulates and things like that. And we build up. You will see it is not that difficult, but it is elaborate, it is sophisticated. It takes time and effort. but it's a wonderful subject. Okay, thank you. That's all for today.